Alright, so hello everyone, and in this particular discussion that we have right here, this is the continuation of the discussion about the nature of light. So, in the first discussion, we talked about the wave nature of light. So, we talked about there how light undergo interference, diffraction, and polarization. Alright, so in this particular discussion, we will talk about what makes a light a particle. All right. So what do you think are the things that makes light a particle? All right. So now in this case, we will focus on one thing which is called the phosphorescence. All right. So this is one example of, or this is one evidence that the light is a particle. All right. So now, how does light fit into atomic theory of matter? Alright, so what makes a light a particle? So, when we define matter, matter is anything that occupies space and has mass. Alright, so how will light fit into something like as small as an atom? Alright, so how will it fit to being a matter? Okay, so in this case, the things that we were going to find out here is to explore the quantum theory of light. So, quantum theory is the other term for the particle nature of light. Okay? And yan, we will try to find out some photoluminescent material which is somehow gives us an idea that light is a particle. Alright, so now, before we start here, there are two ways that the light or that we can transfer energy. One is through waves and one is through particle. Right? So when there is a disturbance, all right, in a medium, right? So when there is a disturbance in a medium, so the waves carries this certain energy and then pass it from one point to another. They transfer that energy from one point to another. For example, sound wave. Alright, so the voice that is coming out from my vocal cords, and it allows the air to vibrate around it. Then this vibration are cascaded through the air, which is its medium, and the air transfers the energy, and then it transfers the energy. Then as it reaches to where it will go. For example, the ears. Alright, so how will our ears respond to that? So the ears will respond to that by vibration of the eardrums. You can hear my voice because your eardrums is vibrating to the sound that, or to the energy that the sound that I have created. So that is by form of a wave. Now, how do you transfer energy by particle? Alright, so when you shoot a particle from one point to another, then therefore that particle contains a lot of energy, and then that particle will transfer that particular energy to its particular target material. Alright, so it doesn't need any medium at all. Right, it doesn't need any medium. All it needs is to move. Alright, move across a certain medium or certain material, and voila, that's it. It can transfer its energy. Alright, so what do we have right here? Now, how is particle nature of light related to, what do we have, what is the relationship of energy, color, and light? So we talked about this one before, that the color of the light corresponds to the energy it gives off. Alright, it was discussed by Max Planck himself, and the color of the light also correspond to the frequency it carries. Alright, so to the frequency. So meaning to say that the greater or the shorter the frequency, or the lesser the frequency, alright, so the greater the frequency, the greater the energy of light. Alright, so what do we have right here? The lowest energy photons that we can see on this picture that we have right here. Yan. So, according to the previous thought that we have right there, so the red is the lowest in terms of energy. So, meaning to say, anything that is colored red, alright, anything that is colored red, it has lowest energy photons. It contains lowest energy photons. Alright, now, as it becomes more bright, as the light becomes brighter, all right, the energy that it carries is starting to increase. So there is a difference in energy between this white light that we have right here and the red light from the stove that we have right here, right? So there's a difference between the energy that they carry. So the more brighter, or the brighter the light, the more energy that it is carried. All right, next one. The energy and intensity of light. So what do we have right here? The intensity of light is the combination of both number of photons and energy per photon. Alright, so how do we distinguish intensity and energy of light? So for example, in red light, the one that we have right here, so in red light, they have so many photons, the one that you see here. So they have so many photons. Yeah. Even though they are made up of so many photons. By the way, what are these photons? These are the unit of light. All right, so these are the basic unit of light. So these are photons, basic entities or basic unit of light. Yeah. All right. So in short, these are some sort of energy packets. Alright, so this photon was described by Albert Einstein himself. Now, the red light contains so many photons, but even though it is made up of so many photons, it contains less energy. Alright, so each photons that we have right here contains less energy, despite they are made up of so many of it. Alright, while the blue one, the one that we have here on the bottom, there are few, as you can see, there are few, but these photons are packed with energy. They are packed with energy. So each photons that you see here contains a lot of energy on it. So it has a lot of energy, right? Unlike the one that we have right here. Alright, so that's the difference. So the more intense the light, the larger energy it carries. But in terms of number of photons, the more intense the light, okay, so in terms of intensity, the number, or as we increase the intensity, the number of photons, right, the number of photons starts to decrease. And together with that, the energy, even though the photons, or the number of photons starts to decrease, the energy starts to, or the energy carried by the photon is greater. Right, now when the intensity, right, so when the intensity is less, when the intensity of light is less, the photons, alright, the photons are many. The number of photons are many, but the energy carried by the photons are less. Alright, so as you can see, intensity and energy are directly proportional to each other. Right, so there we go. Next. Right, now one example that we have right here that makes your light go through the condition of being a particle is that there are some materials which is considered to be glow in the dark. Alright, when they are exposed to light for a longer period of time, and then when you shut down the light, you can see that the light, right, so you can see that the light they absorb is being given off. Alright, so those are the characteristics of a glow-in-the-dark materials. Right, so we call those process of storing light energy as photoluminescence. Alright, so the one that we have right here on the picture, yeah, inside the dark room, when you shine a light, alright, so when you shine a light on a certain material which is a glow-in-the-dark, alright, it absorbs. This material that we have right here absorbs the light for as long as it possible, for as long as the light is present. Then when you turn off the lights, when you turn off this light, then the light that the material absorbs is being given off. Right, so it's being given off. Now, why is this one remain dark? Because this area doesn't absorb light, right? So if this area doesn't absorb light, so what's the point of giving off light if you don't absorb anything, right? So yeah, that's how your glow in the dark materials work, right? Sometimes glow in the dark materials are made up of zinc sulfide. All right, so we have it, the zinc sulfide. All right, so some materials, yeah, so as you can see, it's made up of a metal. Yeah, so later on we will have an experiment on how these things work. Yeah. Okay, so these are some glow in the dark materials. So if you are familiar with these materials, so they absorb light and then they give up those they release of those light energy that they have absorbed eventually, right? All right, so yeah, so almost all atoms or all atoms of different kinds, yeah, absorbs and emit light, but not all of them absorbs at a different or at the same rate. Atoms absorbs at a different rate depending on what atom or what kind of atoms are you talking to. All right, so for most atoms, yeah, the absorption and emission of light happens in less than a million of a second. All right, so it happens so fast. All right, it happens so fast. Now, because of this particular phenomenon, because of this absorption and releasing of light, they thought that the light is made up of a lot of particles. These particles are called photon. Now, Albert Einstein discussed it using what they call the photoelectric effect. All right, now before we go to that, let's have first the idea. What are electromagnetic waves? So, electromagnetic waves, how they are formed? First, they are formed by vibrating electric charges. All right, electric charges, and not only electric charges, also when your electric charge vibrates, it creates a magnetic field. So when electric charge vibrates, it creates a magnetic field. So it can travel through space where there is no matter. Now, even though there's matter, yeah, it can still travel, but it will be affected by what kind of matter this electromagnetic waves is traveling with. Next one, what kind of wave are these electromagnetic wave? Obviously, they are transverse wave. Alright, transverse wave of alternating electric and magnetic field. So, what kind of wave? Alright, so we talked about interference, diffraction, and polarization. So, technically, electromagnetic or light is a wave. Alright, and based on what we have discussed so far, that light behaves as a wave or as a particles. Alright, so basically, these are your electromagnetic waves. Okay, so example or applications that we can use on how wave particle or wave particle dualities of light. One example, especially in polarization part. So, one application that we can use on that part is the 3D glasses. Alright, so the 3D glasses. Okay, with that, yan, we go now to the experiment of Albert Einstein called the photoelectric effect. Alright, so let's go. Now in this simulation that we have right here, so in this simulation, we can see there are two plates on the other side, yan. So on both sides, and it is connected to a battery. Alright, so okay, so on this side there is a target metal called sodium. Alright, so you can no, there will be a link on the description on this simulation. You can change the target material if you want to. Okay, and on this part we have the intensity. You can pull on this slider to increase the intensity, and also there's a slider at the bottom in which you can somehow arrange or select what color of light or what wavelength of light you are going to use. Alright, so let's get started. Okay, so let's start first with the sodium. Okay, So let's start first with the sodium. Now, as you can see, now if we go to the lowest wavelength, all right. So if we go to, sorry, not the lowest wavelength, the longest wavelength rather. So I think this is the infrared region. Now, if we increase the intensity of light, now as you can see, there are no electrons going through. Now, by the way, if this light, or if the photoelectric effect is, if this photoelectric effect tells us that if we shine a light on a metal, it will release an electron that will be captured on this side. Therefore, it will create a current. All right. So as you can see, at a longest wavelength at 100% intensity, there is no electrons. There is no electrons produced on the process. All right. So because lower wavelengths has less frequency, so meaning to say that they carry less energy. All right. So what do we have? What do we have next? Now, if we increase the wavelength, right, so more so if we go to the largest wavelength, which is the blue one, as you can see, there are electrons that are energized. Right, there are electrons that are energized in this particular metal that we have right here. Now, it is captured on the next alright, it is captured on the opposite plate, and it creates a current. Alright, so it will create a current. Now, as you can see, as we increase the wavelength, the number of electrons, alright, so the speed of how electrons are energized are increased. Right, so as you can see, they are from slower ones, right, from being slow, and from the one that we have right here, so they are increased. So as you increase the intensity, but when you lower down the intensity, what happens to the number of electrons? It decreases. Right, so only by increasing the intensity of light and decreasing the wavelength. Alright, decreasing the wavelength means making your light carries a lot of energy. Alright, so by decreasing the wavelength, you increase the frequency, thus increasing the energy. As you can see, there are a lot of electrons that are energized by this light. So this is what they call photoelectric effect. From the word itself, photo means light, electric is the ability to create a current out of these electrons. Alright, out of these electrons coming through a certain material which is targeted by a certain wavelength of light. So that is photoelectric effect, the ability to create electric current using light. Alright, so now if we change the material, okay, if we change the material, it will yield differently. So as you can see, there are a lot of electrons. But not as many as the first one. So the zinc. So we can conclude that the zinc, all right, that the zinc is not good at if we use this one for photoelectric effect. Yeah. So as you can see, the zinc has less electron compared to the sodium a while ago. Alright, now if we put it there, the copper, so the copper as well, the electrons becomes less and less. Alright, so becomes the electrons are diminished. Yeah, and if we use platinum, right, so yeah, there are no more electrons produced. Right? So there are no more electrons produced. So probably the platinum is a metal, right? So it is a metal, and yeah. But as we go beyond, the as we decrease further the wavelength, as you can see, there are a lot of electrons traveling. Alright, so but not as many as the first one. But in terms of the speed on how the electrons travel, this is much faster than the first three elements that we used. Alright, so meaning to say that the electrons in the platinum is highly energized compared to the first three elements we used a while ago. Alright, so more so, if we use calcium, right? So if we use calcium in the long run, so as you can see, although the electrons are few, but the way they travel is much faster than the previous one. Alright, and the current that they create is around is somehow, I forgot to see the current. Yeah. So the amount of current is still the same, right? Still the same because yeah. Okay. So there we go. Yeah. The amount of current is still the same. Why? Because we have the same, or the intensity is constant and the wavelength is the same thing. Alright, so if we lower down the wavelength, so if we lower down the wavelength, alright, what happens to the current? It decreases. Okay, so it starts to decrease. Okay, so with that one, this is your photoelectric effect. Alright, so special thanks to PET simulation, so for this wonderful simulation that we have right here. So without this, we will not be able to see how photoelectric effect works. Alright, so with that one, that ends up our lesson about the particle nature of light. Now, what do you think? Is light a particle or a wave? Or should I say both? Alright, so that ends up our discussion today, and I hope you learned something from this one. So don't forget to subscribe and like if you learned something from this lesson that we have right here. Alright, so don't forget to smile, alright?